section 8.1, discrete time processes in the book. So lesson 26, we're going to talk about section 8.1 of the book, which is discrete time Markov chains. And I'm going to go through the example in the book just to show you some of the things that were calculated in there. Before we do that, let's just talk about what a discrete time Markov chain is. And so if you're given xn, where n is equal to 0, 1, 2, the natural numbers here, we're going to let that be a stochastic process. And what is a stochastic process? It's simply a collection of random variables. So this is definitely a capital N, so I'll keep my notation that I've used in the past. So it's a stochastic process that takes on a finite number of states. Okay, so this is a stochastic process that takes on, okay, so if x of n is equal to I, what this means, then the process is said to be in state I at time n. When the process is in state I, so when the process is in state I, there is a fixed probability of transitioning and I'll go ahead and say from state I to state j. And that fixed probability is p, we're going to let it be p sub ij. So that's a sub bullet there, or sub. So what is that? What is that probability statement? So we're going to come back and just put it in terms of probability. So the probability that we transition to state, so the random variable n plus 1 is equal to j, that we transition to state j given that we were at time n, we were at state I, comma, the time period before time period n, we're going to let that be n minus 1, is in some other state, n minus 1, comma, the time period before that, n minus 2, is equal to some other state, and so on and so forth, all the way till you get back to x, the very first state that you're at some state, right? So we're going to let that be that probability. And so let me write in, this is called, in general, called the future state. Future state. This is called the present, what state you're currently in, so the present state. And this is called the past, or past states. And the Markov property, so the Markov property, so I'm going to say this is equal to, and then give it a little different color here, Markov property states that this probability is simply equal to xn, so capital N plus 1 is equal to j, given that my current state is I, and that's p sub ij. So that's still that same probability that we talked about up here, is that pij. And that's known as, so this is known as the Markov property. So let me put in a little bit more space. We need to talk about one other thing. Let's go ahead and make that go away. So the next thing that we want to talk about with this particular probability is the probability that xn plus 1 is equal to j, given that xn is equal to I is equal to pij, and that is also equal to the probability that x1 is equal to j, given that x0 is equal to I. In other words, these probabilities don't change over time. And what that's known as is time homogeneity. Time homogeneity. And if you have these properties, then you're said to have, you have the Markov property. So let's go down. And then we can do some other things as well. And so let's go ahead and put a couple other things in here. If we have that probability, then the probability going from one state to another is a single stage. I guess that's the next little piece here. So the probability of going from one state to another in a single stage, can be represented by two things: by a state transition diagram, which is probably the first thing that you want to do when you're doing one of these types of problems, because a lot of times it's easy to read the problem and then figure out, okay, so these are my states, and then we'll talk about how to actually do those here in a second, or we'll show an example. But a state transition diagram will be very helpful. And the next thing that we can represent is a state transition matrix. So a state transition matrix. And what that is, it contains the probabilities, that we talked about earlier. P sub ij. So if you had a bunch of state i's and you want to go, or you're trying to figure out what's the probability that I go from I to j, well, this state transition matrix will contain those probabilities. And it's a unique way of multiplying matrices. It's not one that we're used to, but we'll see an example here in a second. Basically, the rows, so here, I'll just put it on here. So the rows represent the current state, and the columns represent the future state. And that's why it becomes a row operation or a row multiplication instead of the one that we're used to in linear algebra doing columns. Again, we'll see an example of those here in a second. So let's move right into the example. So example 8.2 says describe this particular behavior. So let's draw a state transition. So a state transition diagram for this problem. So if x of n is equal to 1, so if we're in state, so we see that we have some sort of state called state 1, then the next state, 1, 2, and 3 with equal probability. Okay, so that means that there's a state 2 and a state 3. And that I have an equal probability. So I can end up with 1/3 probability back in state 1. I can have 1/3 of a probability to go to state 2, or we can have 1/3 of a probability to go to state 3. So 1/3, 1/3. That's what they mean by equal probability. They didn't state it out there. So if I'm in state 2, then I can go back to 1 with probability 0.7. So if I'm in state 2, I can go back to 1 with a 0.7 probability. If I'm in state 2 and I can go back to state, or I can go back to state 2, yes, right, back to state 2 with 0.3. So that means if I'm in state 2, I can go right back to state 2 with a 0.3 probability. And then finally, if you're in state 3, then with probability 1, you go back to 1, or you go to 1. All right, so that's our state transition diagram. This state transition diagram leads to, so this will lead to our state transition matrix. And the way that we want to, I mean, I guess the letter, first of all, that we use to denote that is generally P. And if you let the row, like we said above, if you let the rows be the from, so we're going to go from, I'm going to make this into a matrix because we said it was going to be a matrix. And we let the states above be 2. So we're going to go from 1, 2, 3, 2, state 1, state 2, state 3. Then we can put the probabilities, the piece of ij. So these are your I, here, let me put that in here too. These are your i's and these are your j's. Okay, so what is the probability of, if I'm in state 1, so I'll do this in red. If I'm in state 1, what's the probability that I go back to 1? Well, it's 1/3. If I'm in state 1, what's the probability that I go to state 2? Well, it goes along this line, so it's also 1/3. And then if I'm in state 1 again, then the probability that I go to 3 is this guy right here, and it's also 1/3. So now let's go to from 2, so go to the circle 2. So we're over here in 2, and we want to know what's the probability that I go to state 1. So I'm in, so let me go back over here. So I'm in 2, and I want to know the probability going to 1. So I'll come over here, I look at my state 2, and I say, okay, well, what's the probability that I go to state 1? Well, it's on that line right there. So it's this line right here, so that must be a 0.7. And then we do the same business where we come back over and go, okay, now I'm in 2, and I need to go to 2. So what's the probability there? So it's this one. So it's 0.3. And then we do the same stuff. What's the probability if I'm in 2 that I get to 3? Well, there is no connection between 2 and 3. So we simply put 0. And then we do the same thing with row 3. So row 3, with probability 1, we go back to 1, and then there's no possibility for me to go from 2 to 3. So this becomes my state, this is my P, my state transition matrix. And then we can use this matrix to solve a lot of things, but before we do that, we're going to do it with what you may be used to from your probability class. And so one of the first questions is, maybe suppose, let's see, suppose x, so my very first state was 1. So suppose we start off in x1, or in state 1 in my stochastic process. And then let's calculate, so calculate probability of being in each state. Let's see, man, let's go after 2 steps. So let's do the same thing the book did. So we'll go after 2 steps. You can look at the chart here and tell me what it's going to be for 1 step. For 1 step, it'd just be 1/3, 1/3, and 1/3. But after 2, what would that look like? So the way that we'll do this is sort of a tree diagram, just to kind of make sure that everybody's on the same sheet of music, and maybe everyone's seen this before. So we'll let this random variable equal 1, and then if I'm in state 1, then I can get to state. I can get back to state 1. In other words, my x1 would equal 1 with some probability. I believe it's 1/3. I can get to state 2 with also a 1/3 probability. So this is the time x1 is equal to state 2. And this is my last time. And this is also 1/3. So this is x1 is equal to 3. So if I were just doing this to find the first step, then it'd be 1/3, 1/3, 1/3. That'd be my probabilities. But that's not what it asked for. It said after 2 steps. So now what we're going to do is go back to here and sort of do the same thing that we just did for x0. But we're at x1, and oh, by the way, we're in state 1. So state 1 can get back to 3 different places. 1, 2, and 3. So this will be state 1 again. So this will be the top for time period 2, we're in state 1. This will be for time period 2, we're in state 2, and this will be for time period 3, we're in state. Oh, no, I messed that up. I knew I'd mess this up. It's easy to mess it up. Because we're still in time period 2, but we want to be in state 3. And this one, so if we're in state 2, what different places can I get to? Well, if I'm in state 2, I can only get back to 2, or I could get to 1. I can't get to 3. So I only need to worry about 2 different places. I only need this to be x2 can either equal 1 or x2 can equal 2, but it can't get to 3, so I'm not even going to worry about drawing that line. And then there's only one line that I need to worry about here. This one is where if I'm in state, if you go back up here, if I'm in state 3, so if I'm here, I only go back to 1, so I only need to worry about that line. So this would be x2 would equal 1. All right, so now we need to figure out what the probability. So these are 1/3. This one's 1/3. This one's 1/3. This one is 2. What happens if I go to 1? Let's go back up. 2 to get back 1 is 0.7. So this one is 0.7. This one's 0.3. And the last one down here is 0.1. So what I want to do now is just want to calculate the probabilities, and I'm going to do the green one. So this is the probability that x2 is equal to 1, conditional probability, because this is given that x1 was equal to 1, and then we multiply that one by the probability that x1 is equal to 1, which is equal to, so this was 1/3, this first one is 1/3, 1/3 times 1/3. Now I'm going to only go to the ones that have x2 equal 1, because that's the one that I'm trying to figure out at first. So now in green, I'm going to have the probability that x2 is equal to 1, given that x1, yeah, I didn't put all my capital X's, and I'm going to go back and do that real quick. X1 was equal to 2, because that's what branch that we're on, times the probability that X1 is equal to 2. So this would be 0.7. So 0.7 times 1/3. And then the final one is the probability, because this one also has a 1 on it, that X2 equals 1, given that X1 is equal to 3 times the probability that X1 is equal to 3. And this one this time is equal to 1 now, so 1 times 1/3. So if I'm trying to find the probability that X2 equals 1, well, I have to add up these three probabilities. So I have to add up 1/3 times 1/3 plus 0.7 times 1/3 plus 1 times 1/3. So if you add these all up, you end up getting 0.6777 repeating. All right, so let's do the next one in blue. So what is the probability that X2 equals 2 given that X1 is equal to 1? And that's times the probability that X1 is equal to 1. Same, these should all be the same because we're on the same branch. This is the probability that X1 equals 1. And this one would be 1/3 and 1/3 again. 1/3 times 1/3. And then my final one for X2, because I don't have an X2 at the bottom. And then this would be X2 is equal to 2 given that X1 would equal to 2. Then I got to do the multiplication times the probability that X1 is equal to 2 is equal to, so this probability is 0.3, 0.3, and 1 times 1/3. And we'll figure out what that sucker is. So the probability that X2 equals to 2 is simply 1/3 times 1/3, coming from here, plus 0.3 times 1/3, which is coming from here. So those two put together ends up being 0.21111 repeating. So we have two of them, and then the last one I'll do in red. So the last one is just this simple one right here. The probability that X2 is equal to 3 given that X1 was equal to 1 times the probability that X1 is equal to 1 is equal to 1/3, which we know is 0.111 repeating. So if I was going to summarize all of these, and I can do that in purple here, I would have the probabilities for each one of these particular states. So if I call, so I'm going to let P2 be the probability vector for, so vector, so I'll put a little thing or a little arrow over for each state at step 2. And then we know P2 would equal, let's see, this first one would be 0.6 repeating, and then we get 0.2111, and then we get 0.1111. right? So that would be what would come up. So 6, 7, 8, 9. Okay, yeah, so that adds up to 1. So obviously these probabilities have to add up to 1. Okay, so obviously if we're doing that every single time, it's going to stink. And so what I propose is there's an easier way to do this. And the easier way to do this is going to be letting these be vectors and then using our state transition matrix. So let me go ahead and underline the state transition matrix, and we're going to come back and we're going to use this guy right here in R and help us figure out a quicker way of doing that. All right, so let's see what's next on the agenda. Oh, yeah, we can do it by hand first before we go to R. So I think that's the next thing on the agenda. So if I let P 0, if we said X 0 equals 1, so that's a definite, what does that mean about the probability vector then? The probability vector has a vector with a 1 in it. So state 1, state 2, state 3. So there's 0 probability that I'm in state 2, 0 probability that I'm in state 3, and I'm definitely in state 1 for our pi 0. How would I get pi 1 then? We know pi 1. We know that if we're in state 1, we know what the next step is. So I know pi 1 better be equal to 1/3, 1/3, 1/3, but let's see how we could use our state transition matrix in order to calculate that. And again, I said it was kind of a funky way of multiplying, and so I just wanted to give an example of that as well. So what you have to do is put it in as a row vector. So it's 1, 0, 0. In other words, you got to put pi 0 in, and you got to multiply that sucker by p. So our matrix P, if you don't remember, let me write it down here. So it's 1/3, 1/3, 1/3, 0.7, 0.30, and then 1, 0, 0. So that's our state transition matrix. And then the way that you multiply these matrices together is the same way we've done in the past. It's this row by this column to get our first row. So it's 1/3 basically, right? Because 0 times 0.7, let's see, 0 times 0.7 would be 0. This 0 times the 1 would be 0, so we're just left with 1/3. And then we go do the same thing for this row. For that column, we would get 1/3 again. And again, this row by this column would also give us 1/3 again. So it comes out to what we would expect it to be. So this is equal to the probabilities of being in each one of these states. The next thing we want to do is use pi 1 to find pi 2. So as you can imagine, if you're sort of following along here, then our second step, if you will, is going to be equal to pi 1 times p, which would be 1/3. It's not going to be quite as easy this time to calculate, but that's fine. We can muddle our way through it. And hopefully we'll see a pattern that looks something like what we've already done above us. So 1, 0, 0. And that's equal to, so these would be row vectors. So the first row would be pi 2, 1, if you will. So it'd be the first element in the pi 2. So this is pi 2. It would be a vector, and I'm going to let this be pi 2, 1, this one be pi 2, 2, and this be pi 2, 3, representing the first element, the second element, and the third element in this vector. So we'll let pi 2, 1 equal, and again, it's this. So let me go ahead and, so it'd be this row times this column. So let's see what we get. 1/3 times 1/3 plus 1/3 times 0.7 plus 1/3 times 1. And so that would be the probability in the second step. So the second step of state 1. So let's go back up and make sure that makes sense from above. Oh, look at there, it's already on our screen. So 1/3, 1/3, so this 1/3, 1/3 corresponds to this first one. The second one, 0.7 times 1/3 corresponds to the second one. And the third one corresponds to the third one. So we know we're getting exactly the same answer that we did before, 0.6777 repeating. And then pi 2, 2, again, second step, second state would be equal to what? Well, I'm going to take this 1/3, 1/3, 1/3 row, multiply by the 1/3 0.30 column, and we get 1/3, 1/3 plus 1/3 0.3. And again, we'll move back up just for a second. And this is the 1/3, 1/3, 0.3 times 1/3. So we know this one is 0.2111. And then finally, the last one is just 1/3 times 1/3. So we know that this row times this column is just going to be 1/3, 1/3. So that makes a lot of sense. So hopefully you're following along that all we did is just some matrix multiplication. Now it's a weird one where we're putting row vectors and multiplying by a matrix, but it shouldn't be that crazy because it is the same type of stuff that we did in linear algebra. It's just, it looks just a little different because we're doing row vectors instead of column vectors. Okay, so my pi 2 would end up being the same as it was above. Same as above. Did I write it above? Yes, I did. So it's the same one that was here. All right, so obviously we're going to have to be able to do this a lot. And so let's go ahead and look at R to see how we would go about doing that. Okay, so R, go ahead and put lesson 26 notes. And we'll let P be our matrix. And then it's just 1/3, 1/3, 1/3. And 0.3 and 0 and 1, 0, 0. And then you got to remember to tell it that the number of rows is equal to 3 and the by row is equal to true. And then we'll put a semicolon here and just tell it to print just to make sure that it looks exactly. And it does. So we got the 1/3 across the first row, points, and everything adds up to 1. Remember, the rows have to add up to 1 because if you're in a state, you're gonna have to go to some next state. So with probability 1, you're gonna transition you could transition back to yourself, and that's fine. But with probability 1, you're gonna go from one state to the next. Okay. Pi 0 is equal to that's the one where we said it was the 1, 0, 0. And then we let pi 1 equal to, let's see, pi 0 times, and it's not just a regular times. Remember, you got to give it this little percent times percent for it to do matrix multiplication. And believe it or not, R knows if you put it on the left-hand side that you're doing row. So it's pretty smart. And then tell it to print. And that's what we got for pi 1 earlier. So we'd expect, and hopefully that's what we expect. And then obviously pi 2 would equal to pi 1 percent times percent P again, and then print pi 2 And hopefully that's what we got earlier by doing it by hand, and it is. Okay. And then you could sum pi 2 if you just don't believe me that it's equal to 1 pi 2, and it is equal to 1. Okay, I don't really need that, but I just wanted to show that. Okay. Or we could do something a little different. So I'm going to put this new little function here that I'm going to create, just because I don't know if there's a very easy one to do without including some kind of library. But I want to do a matrix multiplication. You would think that maybe matrix multiplication has this percentage sign on it, but it doesn't. So let's just create our own little matrix power function. We're going to end up putting in R for our own benefits, right? So let's see, equals, we forgot the equals function m comma n. We'll let n be the number, the power that we're going to take it to. Okay, m is going to be our matrix, and so what we're going to do is m0 equals our matrix. Then maybe a for loop here, so for I n1 through n. So we're going to do a bunch of these matrix multiplications, and then what I want to do is say, well, m is equal to percent times percent m0. Okay, so what we're doing is we're going to hold in, so if I did this twice, I would go, so from 1 to 2, m is equal to m0. So if I take it to the first power, we'll have to come back and make sure that it's doing what we want it to do. Maybe we go from 2 to n, 2 to 2. Let's just do some experimentation here and see what it gives us. So we're going to return m, control enter, and matrix power e comma 1. Let's do 2 first. So is that, and then percent, let's see. Oh yeah, so we might need to go for 2 from, let's see what it gives us. So 1, it doesn't give us the right thing. So let's go ahead and make this go 2 for and see what happens now. For I n, so it looks like it multiplied it at least once. Maybe if n is equal to 1, and we got to put a parenthesis around it. So maybe if n is equal to 1, let's return n. Let's see if that one works. Okay, all right, that's a little bit better. All right, so if it's equal to 1, then it just returns itself, which is what we want. And then if it's 2, then it multiplies. So let's see what happens when I do C of 1 comma 0 comma 0 matrix time. And we get what we had before. Okay, so that works. So if I wanted to the 3rd power, all right, so if I wanted to the 4th power, if I wanted to the 10th power, all right, what's happening as I'm making this bigger and bigger and bigger? Maybe to the 100th power. All right, so we see that the probabilities are going to some number, and they're not changing. So what that leads us to believe is there's some kind of limiting probabilities for a matrix. So for any particular probability transition or state transition probability matrix, there's probably some probabilities. There's probably some probabilities. So there's some probabilities that we are going to if we increment this thing enough. So let's go back to our math over here. So let me stop sharing this, start sharing here, and let's define these limiting, sometimes they're called steady state probabilities. So I can start off with that. I think in the book he calls them steady state probabilities. And then in some books you'll see them called limiting probabilities. If I say limiting, that's a mean steady state. So I'm gonna try as much as possible to remember the steady state probability, but I learned it as a limiting probability. So just know that that's what I mean by limiting probability. Okay, so what we're talking about here is if you take the limit, maybe as n goes to infinity, of wherever you start, doesn't really matter where you start. If I take p large enough, then I'm going to get this pi star that is a steady state probability. All right, so a way to find these, all right, we'll see how to do it in R here in a second, but here's what we're going to be doing basically. So the way we find these probabilities, so the probability of being in any particular state, right? So over the long term, this one looks like it goes to 5% of the time we'll be in state 1, 26% of the time we'll be in state 2, and 18.4% of the time we'll be in state 3. So the way that we find them is this. So pi is equal to pi times p. So once we solve these equations, the deal is we'll get an infinite number. So if you just solve these sets of equations, you'll get an infinite number, but then we add on the fact that we know the sum of pi yeah, let's do that. Let's say they call it the sum from I is equal to 1 to, let's see, it's not n, we can't use that one anymore. The number of states, however many states you have, of pi sub I is equal to 1. So basically what we're saying is just add up all the probabilities and they got to be equal to 1. That'll be another row, if you will, that we'll put in, and then we'll solve this system of equations in order to get what the steady state probability is. Okay, so let's see what happens. So let's do the one for this particular problem. So we get, call it pi 1, pi 2, pi 3, and that's equal to pi 1, pi 2, pi 3 matrix multiplication. And we'll go ahead and put in the matrix that we had from before, and we'll figure out how this thing got 0.55 and 0.26 and all that. So this would be 0.7, 0.3, and hopefully you remember your linear algebra, because we're going to be finding a null space, everybody's favorite thing to do. So this multiplication here gives me, so pi 1, pi 2, pi 3 is equal to a row of 1/3 pi 1, pi plus 0.7 pi 2, and then plus pi 3. All right, that's the first piece, first component, and you're going to see why we usually do column operations, because this row is going to get unwieldy, and we'll turn it into a column multiplication just by moving some things around. Okay, so that's the first element that's in that row, and the next one is this row by the second column. So the pi 1, pi 2, pi 3, and we're going to be multiplying it by the second column. So this one times this second column here gives us our second row, and that will be 1/3 pi 1 plus 0.3 pi 2, and then plus 0 pi 3. And then our last row is 1/3 pi 1 plus 0 pi 2 plus 0 pi 3. And there's a reason why I'm putting the zeros and leaving those suckers on there, but we'll see that here in a second. Okay, well, let's change this thing up to make it columns. And so the way that we do that is simply do the transpose of both of these. So if I did the transpose of both of these, I'm going to write it 1/3 pi 1, just because that's the way we're used to seeing null space. I mean, we could do this the other way as well, but it's not maybe it wouldn't be as familiar to some of you guys as this way. So pi 2 plus 0 pi 3, and then 1/3 pi 1 plus 0 pi. I should have just changed this to a matrix too. I should have done all that at the same time, but maybe this will be helpful if we is equal to, so we took the transpose of both sides, pi 1, pi 2, pi 3, and then I'm going to subtract. So I'm going to take this and subtract it to the other side. And then, so that'll be negative 2/3 pi 1 on the first row, and then plus all the other stuff remains the same. All the other pieces. And then 1/3 pi 1 minus 0.7 pi 2, because we took this one and subtracted it from this. We took this and subtracted it from that piece. And in a second, we're going to take that and subtract it from that. So then we get plus 0 pi 3. All right, just keep rolling here. And then subtract 1 pi 3. All right, and all that, because we subtracted it from both sides, right? So I subtracted this piece, this guy goes to 0. So it's the 0 vector, 0, 0, 0. Okay, we're sitting at a spot where we want to change this to matrix multiplication. So I'm going to change this to matrix multiplication, and then, so matrix multiplication, and then we're going to null space. So it just becomes negative 2/3, 0.71, 1/3, negative 0.70, and 1/3, 0, negative 1. All right, and then 0, 0, 0. Right, so that means we're finding the null space, and then now we can move some things around. So I'm just going to I'm going to multiply, move things around, sort of at how I want it to look. And so all I'm going to do is take this one and put it at the top. Right, and then I think I'm going to take this one and put it on the bottom, and I'm going to multiply it all by 3. So I get 1, 0, negative 3. The 3 elementary row operations are we can move our rows at will. I can multiply any row by some number, and then I can multiply any row by a number and add it to another one. So right now I'm just utilizing the fact that I can multiply and move things around. So this would be negative 2.1 because I just multiplied this row by 3. And then I get 0, so all these are still 0. And then this one moves to the bottom. We multiply it by 3, and we get 2, 2.1, 3, and 0. Okay. The next thing I'm going to do is simply multiply this row by a negative 1 and then a 2. So I'm going to multiply this row by a negative 1 and add it to the second one. So I get 1, 0, negative 3, 0, and then 0 here. Negative 2.1, and then a 3, and then a 0, and then multiply this guy by 2 and add it to the last one, and I get 0, 2.1, negative 6 plus 3 is a negative 3, and a 0. All right, And the next thing I noticed is that these two rows are the same, basically. You can multiply. So if I multiply by 1, or if I just added them together, I would get a bunch of zeros. And so I note that, and I can just turn one of the rows, and I'll just make it the bottom one. I'll turn them into a bunch of zeros. So 0, 0, 0, 0, and then 1, 0, negative. So this all the other two rows stay the same. I'm going to go ahead and multiply that by -1, so I get 2.1 here, -3 there. All right, so we're almost done here. Because now what I want to do is I want to get a 1 right there, and that just means divide through by 2.1. And so if you do that, you end up getting 1, 0, -3, 0, 0, 0, 0, 1, and then it's -3 over 2.1 or -30 over 21. Doesn't matter how you write that. And then a bunch of zeros. So now I know that my null space is any vector. So pi, I guess I shouldn't do pi. We'll just do v for right now. We'll do v. Oh no, I'll do pi. Let's call it pi. So the pi vector is equal to sum. So this is my free variable. So we'll just set it equal to 1. If that's 1, then that guy must be 30 over 21. And that guy must be 3. But we know it's all of these. So right now there's an infinite solution of these. But we're going to add that piece where we know that pi 1 plus pi, here let me call this pi star. Pi 1 star plus pi 2 star plus pi 3 star, we know is equal to 1. So I know that 3c plus 3021c plus c is equal to 1. And let's go ahead and convert all of these to have a 21 in the denominator. So that means what? 63 over 21c plus 30 over 21c plus 21 over 21c is equal to 1. And then let's add the top. So what do I get? 93 plus 21. 93 plus 21 is that 114. So I get 114 over 21c is equal to 1. Therefore, c must be equal to 21 over 114. All right. So if that is my that's my c that must go on to this vector in order for it to satisfy the equal 1 piece, then there's only one of these pi stars, right? So pi star must equal to 3 times 21. So that would be 63 over 114. The next one would be 30 over 21. I'm gonna have to multiply that sucker out. So it'd be 30 over 21 times, oh, okay, never mind. Look at that, it cancels out for me. So it would be 30 over 21 times 21, so it would be 30 over 114. And the last one would be 21 over 114. And hopefully 63, 93, yes. So this adds up to 1, and I believe if you put this in your calculator, this better come out to what we thought they should. So I'm going to go to R real quick. I'm not going to bore you guys with this, but 63 divided by 114, control enter, is 55.26. So 0.5526. 30 divided by 114 is 0.2632. 0.2632, and then this one would be 0.1842, which is exactly our limiting probabilities that we were getting before. All right, that's all we got for today. Go back and review the text and make sure that you understand where they were coming from in their examples. Next class, we're going to be working some of these problems, and I'm going to go back for lesson 27, and I'm going to give you some videos to review in order to get some of these conditional probabilities and those sort of things if you're still struggling with that. All right, that's all I got.